Welcome to the Abby and Eva Informative. Today we're going to be learning about Lewis structure and VSEPR Theory. On a more serious note,
let's get into the overview of what we're learning today. Today we will be learning how to draw a Lewis structure, how to draw a complex Lewis structure, and how to determine molecular shape and VSEPR theory. First off, we're going to start with steps for drawing a Lewis structure. The first step is to count all of the valence electrons. Second is to determine the central atom. This is the element there is usually only one of. 3 is to draw single bonds to the central atom. 4 is to put all remaining valence electrons on atoms as lone pairs. The last step is to turn lone pairs into double or triple bonds to give every atom an octet.
Let's apply these steps to the Lewis structure of the molecule N2. The nitrogen atom has 5 valence electrons, and as we have 2 of these, that gives us 10 valence electrons. The first step is to draw a single bond between them. Do you remember how many electrons are shared in a single bond? That's right, it's 2. That means that we have 8 valence electrons left. The next step is to draw the remaining valence electrons around the nitrogen atoms. In order to give both nitrogen atoms a perfect octet, we're going to turn 2 pairs of valence electrons into double and triple bonds. As they share these bonds, both nitrogen atoms will have a perfect octet, as they are sharing 6 and both have a pair of 2, making them happy.
Pause this video and try drawing the Lewis structures of O2 and F2 yourself.
Check your answers with a quick run-through of these problems.
Now let's look at the Lewis structure of CO2, a little bit harder of a molecule. First step is to find the valence electrons. Carbon has 4 valence electrons. O2 has 6 times 2, which equals 12 valence electrons. 4 plus 12 equals a total of 16 valence electrons. The next step is to find the central atom. This is going to be carbon because there's only one of them. We are then going to add single bonds to each oxygen on either side of the carbon. The next step is to put all the remaining valence electrons on atoms as lone pairs. We have 12 because we used 4 in the single bonds. We are going to then add double bonds between the oxygen and carbon to give each atom an octet. This is the final diagram of CO2, which gives them all 8 electrons and makes them happy.
Now let's look at the steps for drawing a complex Lewis structure. The first thing we're going to do is figure out how many bonds each atom wants. Step 2 is to put the atom that wants the most bonds in the middle, making it the central atom. Step 3 is to give each atom the number of bonds it wants. And the last thing we're going to do is add lone pairs where necessary to give each atom an octet. Now let's practice the more complex Lewis structure of NH3, which is ammonia. The first thing we're going to do is figure out how many bonds each atom wants. As hydrogen only has 2 valence electrons, it will only form 1 bond. Nitrogen has 5 valence electrons, so it's going to form 3 bonds. That means that nitrogen wants the most amount of bonds, so we're going to put nitrogen in the middle. Now we're going to put nitrogen in the middle and draw single bonds to each hydrogen. As nitrogen still has two more valence electrons, we're going to put them as a lone pair on the molecule. Never give a hydrogen a lone pair, as it only wants two valence electrons.
Pause this video and try drawing the Lewis structures of COCl2 and BH3. Check your answers with a quick run-through of these problems. For the correct Lewis structure of COCl2, make sure to add a double bond to oxygen because it leaves carbon with 4 bonds, which is what it wants, and gives it a perfect octet.
You may think boron needs 8 pairs of valence electrons, but as you can see from our calculations above, it only needs 6.
Now that we're over the hard stuff, let's get into the easier part. Let's put easier in quotations. Come along as we learn VSEPR Theory and molecular shape.
Next, we're going to look at how to determine molecular shape. The first step is to draw the Lewis structure of the molecule. The second step is to count the number of things on a central atom. By things, it means bonded atoms or lone pairs. The third step is to look at the rule, things repel and get as far away as possible. The fourth step is to look at the rule, lone pairs occupy more space than bonds. Let's determine the molecular shape of SO2 and CO2. The first step is to draw the Lewis structure of the molecule, which is what we learned in the previous lesson. The second step is to count the number of things on the central atom. The single bonded oxygen is a thing, the double bonded oxygen is a thing, and the lone pair on the sulfur is a thing. The next step is things get as far away as possible. The 3 different things will repel against each other, creating more of a bent shape. The last step is that lone pairs occupy more space than bonds. This means that the bond angle is going to be 119 degrees and the final shape is going to be a bent shape. Now let's try to determine the molecular shape of CO2. The first step is to draw the Lewis structure of this molecule. The second step is to count the amount of things on the central atom. Each oxygen is going to be a thing. The next step is that things get as far away as possible. Because there's no lone pairs on the central atom, these things are already as far away as they possibly can be. Because there is no lone pair on the central atom, the bond angles can be 180 degrees. Therefore, the shape of CO2 is going to be linear.
Determining the VSEPR shape of a 3-atom molecule is fairly simple. The first question you must ask yourself is if it has a lone pair on the central atom. If yes, that means it's a bent molecule. If no, that means it's a linear molecule. Let's look at some examples. As you can see on the example on the left, there's a lone pair on the central atom, causing the other 2 atoms to be pushed away from the lone pair and towards each other, causing it to be bent. The example on the right does not have a lone pair on the central atom, and it is linear.
Let's look at how to determine the molecular shape of a 2-atom molecule. It is very simple, as 2-atom molecules do not have a central atom, which means they cannot have any bond angles. So the only shape is linear for 2-atom molecules, like the example N2 shown here below.
Next, let's look at a 4-atom molecule. If it has a lone pair on the central atom, then that means it is trigonal pyramidal. If it does not have a lone pair on the central atom, it is trigonal planar. Now let's look at some examples of these molecules. In our previously stated diagram of BH3, we know that this is correct in terms of bonds, but not structurally correct. As the hydrogen bonds want to repel away from each other as far as possible, they take on a more triangular shape, with a bond angle of 120 degrees, giving it a trigonal planar shape. In NH3, we're going to draw single bonds to the hydrogen atoms and have a lone pair on the nitrogen. As lone pairs take up more space than regular bonds, they are going to repel the hydrogens farther away from it. This also causes it to take on a more triangular shape with the hydrogens farther away from the lone pair, making it trigonal pyramidal.
Lastly, let's look at 5-atom molecules. Most of the time, these are called tetrahedrals. There are some exceptions, but we are not going to look at those today. Let's look at an example of a 5-atom molecule, CH4. Carbon is in the middle with 4 single bonds to hydrogen with no lone pairs. There are 4 things on the central atom, and each of these will repel against each other to be as far away as possible. This is a 3D model, so the bond angles are going to be 109.5. The ending shape of this molecule is tetrahedral.
We challenge you to draw the Lewis structures of baking soda and vinegar.
P.S. They're at the beginning of the video.